Well, hello again. In this example, you will learn how to take the output given by the matrix approach and use it to generate shear and moment diagrams for beams. We will be specifically looking at this two-member beam where we are already given the member end forces that would be computed as per the matrix approach. We see those down here, and in order to help us understand that, we need to have the degree of freedom labeling. So we have the unrestrained degrees of freedom here, 1 and 2, and the restrained degrees of freedom here, 3 and 4, 5 and 6. I need to remind you that these quantities that are given below are given in what we call the matrix sign convention. Now, as a reminder of what that sign convention is, I will come over here and indicate that that is a positive shear when I have an arrow on the left end of the member, and a positive shear here when I have the arrow on the right end of the member. Positive moments are these counterclockwise moments as such. However, in order to generate shear and moment diagrams, we're going to have to convert from the matrix sign convention into a beam sign convention, which says that a shear that causes a clockwise rotation of the member is going to be positive, and that moment arrows that point to the top of the member are going to be considered positive. So the ones in particular that we need to watch out for are these, because they will have opposite directions for the same sign. We also need to pay attention to these because they will have opposite signs for the same direction as well. If we are going to plot the shear moment diagrams, it would be helpful if we actually created equations for the internal shear and moment in each of these members. First thing I'm going to do is I'm going to sketch a free body diagram here, which will place the shear and the moment on the diagram according to the sign convention for the matrix formulation. The process for generating shear and moment equations is we need to have an origin for the member in terms of x. We will come out a distance of x and we will make a cut. We will then sketch the free body diagram for that, recognizing that we have come out this distance of x, making that cut. We have these forces on the end, V3, M4, and then we have these internal forces, the internal shear here at the distance of x, and the internal moment here at the distance of x. And what I'd really like to point out to you here is that when I sketch these on here, I am using the beam sign convention, so that my moment and shear diagrams come out appropriately. I can then use the sum of forces in the y equation to go ahead and get me the equation for the shear as a function of x, and that will simply be equal to this quantity of V3. I can then write a sum of moments equation to get this moment as a function of x is equal to V3 multiplied by x minus M4. So you'll notice in this that in order to get the two equations that I need to plot, I really only needed these two values. Now these equations are not completely valid until I provide a proper domain. So let's come back here and just identify once again that here is my x quantity. It's 12 feet long, but I developed those in units of inches, and so my proper domain is going to be 0 to 144 inches. And I will then go into my spreadsheet and plot these equations. I then do the same type of thing for member number 2, coming out this distance of x, making a cut, and then sketching that free body diagram in terms of those unknowns. And that free body diagram will look as such. Sum of forces in the y will then reveal a shear equation that is equal to V1. And sum of moments will equal a moment equation that is equal to V1 times X minus M2. Now, a really quick point to make here is that, once again, the only terms we used in these equations were like this. And in fact, if you look at member number 1, you'll notice that there is a pattern that has been established here. And that pattern is repeated here. In fact, that is exactly what you can do for every member, no matter if I had 5 members, 10 members, 20 members. Those equations are going to be of that form. So in a spreadsheet, I can go ahead and plot these equations for each of these 2 members. I have gone ahead and shaded in these regions just so it's a little bit easier for you to see what that shear and moment diagram looks like. But specifically, let's go ahead and look at how that physical plotting is being done within the spreadsheet itself. So recognize that in member number 1, all I needed were these quantities, V3 and M4. For member number 2, I needed V1 and M2, as had been given to me. I can plot those equations as a function of X, and I just go ahead and discretize up that 144-inch long member into enough pieces so that I get decent resolution in that equation. Then the implementation becomes as simple as this, that when I need to identify what the shear is, it's nothing more than making it equal to what that V1 quantity is. And by the way, what I'm showing you here is for member number 2. And for the moment equation, you'll notice that that is the V1 term multiplied by my X value right here, subtracting off the M2 value. Now, one of the things you're going to notice here is you've got this extra column, and we do need to address that. Member number 2 has this extra column, which I have labeled as a capital X, and that is as opposed to a lowercase x. I want you to think of lowercase x as being the local coordinate system, so that is where the member begins, just like we had done here. I want you to think of capital X as being the global coordinate system, meaning if we come back here to this original thing, we have a coordinate system that comes out here as this capital X and can describe the entire length of the beam. If you don't use a global coordinate system to do these plottings, then what will happen is you will get this to plot right here, and that most certainly is not what that looks like. So essentially, just look at this as being an offset. You'll notice what that offset was is nothing more than a 144-inch offset, so that in the local we had 144, in the global that was 288. I used these quantities to calculate this and this. But when I plot it using the global system. And once again, providing me with these shear and moment diagrams. That concludes this example. As always, it's a beautiful day for studying structures.